It's an honor for me to be here. I remember that when I was a smaller kid than now, so about 40 years ago, I read your first book. I was very impressed with these gods writing these books. And it's now a pleasure to be back 40 years later and give a talk here in this nice conference. So thank you and congratulations with your birthday. I'm talking about set-theoretic solutions, which sounds like very far away from what the heck is going on here. But I'll try to keep you awake during the lecture and end up with group rings. And then some of you might wake up, hopefully, again. But I hope to get there, which is a problem. I'll start with the introduction and the motivation, what I'm doing. So the main item here is the Yang-Baxter equation. And what is that? You take a vector space over a field K, and then you look for mappings R from the tensor product of V to V. Such that the following equation is satisfied, such that, and rather in this order, R tensor the identity, identity tensor R, then R tensor the identity is equal to this manner. So in other words, the braided relation has to be satisfied. And it was a question posed by Yang and Baxter, comes out of physics, but don't ask me any physics questions because I will not be able to answer you, but it's apparently the motivation. It's also used in Hopf algebras and quantum groups. They want the solutions for this R. Which mappings R satisfy this? Now, this seems to be a very complicated matter. And so Drenfield in 1992 tried to look for simpler solutions. So a solution here is a solution of the Yang-Baxter equation. And he looked for the simplest solutions. What is the definition of simple here? Well, you take a basis, say X, and you look for mappings R. Oops. You look for mappings R, and I will denote them a little r, which are mappings from x squared to x squared, such that this identity is satisfied, but now replacing the tensor product, you look for a mapping R such that R times the identity, and this is now on x to the third you act. So this means you act with R on the first two coordinates and the identity on the third coordinate, and you want this to be satisfied. And you want such mappings so that if you extend them linearly, you get solutions here. So you reduce to the basis and try to find solutions on the basis, and those you can extend, you get solutions there. And these are called set-theoretic solutions. And so Drenfield posed question, describe all such R. And in his original paper, I seem to remember that he mainly was interested when R is bijective. First interest is R is bijective. But you don't need that. Recently, in a paper by Lebet, he is a lot interested in when R is idempotent. Her reasons are for knot theory. These are applications in colorings of knots. Let me give you a couple of trivial examples, because it's relevant for later. Okay, the first trivial example is R is the identity mapping. Of course, it satisfies this stuff. It's a solution, but I'll tell you later that this is a very bad solution in some sense. The second one is the flip map. To verify, you interchange x and y for x and y, and x satisfies this solution. Third one is the dihedral solution. What you do here is you take the dihedral group of order 2p, generate by A and B, standard presentation, and you take for x the set of elements of order 2. And now you use conjugation as follows. So if you take two elements of the dihedral of this set, x and y, then you say you act via conjugation this way, and here you put x. Okay? So I'll introduce the notation here. The image of x and y, I will use it denoted by lambda x of y, rho y of x. First coordinate depends on x and y, I denote it this way. So here, in this situation, lambda x of y is equal to x, rho y of x is equal to y. They're constant maps. Here, lambda x of y is equal to y, rho y of x is equal to x, so they're the identity mappings. Here the mapping is, the first one is conjugation. Okay? Another one is the following. I take a set on two elements, x and y, and I use a transposition that flips x and y. And then you define R of xy equal to xy, R of yx equal to yx, R of xx equal to yy, and R of yy equal to xx. And later I'll see why the sigma is important. This also satisfies this thing, and this is a special case of the following situation. Take x, you take a sigma in the symmetric group on x, you say R of xy is equal to sigma y, sigma inverse of x. That's also a solution. These are easy things. Now, my motivation is a paper by Ehngogff, Solaver, and Schedler, was in 1997, I think, or 1997, and Kateva Ivanova, Michel van den Berg, in 1997. And they looked at solutions where all lambda x are bijective, and one calls the solution then left non-degenerate. If all rho x are bijective, one says right non-degenerate. And degenerate means lambda x and rho x are bijective. They also looked mainly at this case where R squared is involutive. Involutive. Okay. Before I can state what they actually did, let me say, introduce now three objects associated to the solution. The first is the structure monoid. I'll denote this with M. It's the monoid generated by the set X with relations xy is equal to lambda x of y, rho y of x. So this is the image of under the R map that you use. That's the structure monoid. That's what Van den Berg and Gateeva were interested in. Ehngogff and Solaver, they looked at the structure group. I'll denote it by G. And this is the group with the same presentation, but as a group. You have to be careful if you work in the group. Some of the letters might become identified in these things. That doesn't happen in the monoid. And then you have the structure algebra. And when I talk about algebra rings, I mean associative rings with an identity. This is A over a field K denoted like this. And actually, this is nothing else than the monoid algebra. That means the algebra generated with that presentation. Okay? Now, note that all these things are graded objects by the integers. Because the relations are homogeneous of degree 2. Okay? Now, what is my motivation? In their paper here, Van den Berg and Gateeva proved if it's non-degenerate, involutive solution, and bijective, well, that is obvious if it's involutive, then this is a very nice algebra. Because I have to define what nice means. The philosophies, they behave like commutative polynomial algebras. So for example, the group algebra, or the monoid algebra, is a domain. That's a statement, that's not obvious. It's Noetherian. It's PI. It's a maximal order. And keep going. Then basically any homological property in commutative polynomial algebras, and it's satisfied. The structure group in the same case is a Bieberbach group. Finitely generated, torsion-free, solvable. So these groups are solvable. That's also a statement. Okay? That is my original motivation. For me, these are quadratic algebras. And they're Z-graded, defined by homogeneous relations of degree 2. They're quadratic algebras, and they have a very nice arithmetical structure. They behave like UFDs in some sense. So that was for me good enough motivation. But that's why I wrote the examples down. If you look at this algebra, what does this give? This is the monoid with what is the relation? Well, you do nothing. The relation is xy is equal to xy. So in this case, the monoid is the free monoid. The algebra is the free algebra. And you cannot expect those properties I wrote down there for the free algebra. In this case, with the flip map, this is the free abelian monoid, if you do it on 2 letters. And the algebra is a UFD. In this case, it's a bit more complicated. I'll come back to that later. And this is an interesting case. If you write down the relations, the only real relations, xy is xy, yx is yx, x squared is y squared. Y squared is x squared. So it's xy, x squared is equal to y squared. An interesting monoid. You can take, the monoid is embedded in a group, and it's an interesting algebra. We'd say for a tutorial session, go and play with it and prove that. Might not be so obvious to do. Okay. So what I want to do in this lecture is to report on some results. And I see that time goes fast, so I don't want to say too many. But let me report on the results that answer some questions of Gateeva Ivanova. And this is joint work with Lucas Kubat and Arne van Antwerpen. So what one does to study this algebra, Km, you first associate another monoid to M. So there is an associated monoid. Which is denoted by AXR. There's no field involved here. And what is the monoid? Again, go with the same generating set. You have your solution, which is R, I'll assume it's left non-degenerate. All I need. And I use these relations. Lambda y rho yx. You use the solution to define a new solution. And what you do here is you rewrite this with the mapping R. And you rewrite it again with the mapping R. Then you get here, don't make mistakes. And what is the new relation? You relate this thing, and you make it equal to this thing. Looks like fun to do, but this is very relevant. This monoid, you can of course rewrite as XX. Since it's a non-degenerate, this is a bijection. So you can rewrite this also as XZ is equal to Z, and you have a new mapping, sigma of ZX. And you see, I can flip letters over a letter, and I keep this letter, and this changes. So this is a monoid, so that for every A in A times A is A times A. But one often says all the elements are normalizing elements. Looks like a bit of a commutative flavor. In ring theory, this is a very useful property. I'm a ring theorist from birth, so I like to use this. Okay. Now, what is a proposition? These two are very strongly linked. So what you have is, I'll try to write it in a nutshell. There exists a bijection, I'll denote it here, F, from M to the semi-direct product of this monoid A, so this is AXR. And this is the group generated by the lambdas. This is often called the permutation group of the solution. And this monoid is such that the image is a regular submonoid of the holomorph of this. So it means that the image can be written as the first coordinate determines the second coordinate. And I'll denote this as phi of A. So it's a regular submonoid of the holomorph of A. Or for those who prefer cohomology, you get a one cocycle from M to A. And using this one cocycle, you can define a new operation on M based on the operation here. This is in a nutshell, but I don't, because of lack of time. So let me now show you a result. It tells you that that behavior there happens a lot. The theorem by myself, Kubat, Antwerpen. And it's already available on the online on the transactions. And it says the following. So XR is here, we assume it's finite, which means X is finite. Bijective, the R left non-degenerate, solution of the Yang-Baxter equation. Well, then there exists a finitely generated commutative submonoid. I've called it here T. M. We know more about that than this. And the finite set F M such that this monoid is like a finite module. It's a union over this finite set of cosets in some sense. You can use left or right ones. So F is a finite union of something that is abelian and finitely generated and finitely made a coset. So if I go to the algebra, that's a finite module, left or right, over an affine algebra A. Hence, it is PI the theory. Furthermore, you can prove that the classical Krull dimension is equal, it follows automatically, to the Gelfand-Kirchhoff dimension of the algebra. And you can prove this is equal to the rank of M, is equal to the rank of A, is equal to the classical Krull dimension and the Gelfand-Kirchhoff dimension of the algebra over A. The rank of M is the number of generators of the largest free abelian submonoid. Number of generators of the largest free abelian submonoid. So this behaves very nice, and this rank will be at most X. Okay. As a corollary of this, you can also do the following. By the same authors. So the motivation is you look at Km, it's a Z-graded ring, even an N-graded ring. Those are the components of degree N. Since the one co-cycle that I use from M to A, you can show, I forgot to mention this mapping here sends a generator, or a generator here. If you look at the X here, it corresponds exactly to the X there. So what you do is you send X to some X comma lambda X. It preserves degrees. If it preserves degrees, if I want to prove something about the size, the dimension of the homogeneous components, I can do this as well in A. And A is a nicer monoid. So it's easy to compute the Hilbert series for Km from that of Ka, but Ka behaves a bit commutative. That is used in the following result. So you assume here XR is finite, bijective, left non-degenerate. Solution of the Yang-Baxter equation. Then the following are equivalent. XR is involutive. So it's the situation considered by Ehngogff, Schedler, and Solaver, Kateva, Vanova, and Van den Berg. It's equivalent with the monoid is cancellative. You can cancel elements. If you don't like this, it sits in a group in this case. You can translate this into the monoid A is cancellative. sits in a group. The rank of the monoid M is exactly X, the maximal possible. The rank of A is the maximal possible. And then more funny is it's equivalent with Km is prime. It's equivalent with Km is the domain. Prime and domain are the same here. The classical Krull dimension is the maximal. The Gelf-van Kirchhoff dimension is the maximal. But let me finish with the last one. The dimension of the degree 2 component is the maximal possible, is equivalent with this. And the maximal possible, if you think of that, in A, in some sense you can interchange letters, but you have to adapt them. So you can choose an order on the letters and you can put it in the right order. And then you get the number of words, which is exactly the number of words in the commutative free abelian monoid. So the maximal possible is this number. X choose 2 plus X. So the dimension there determines structure on the algebra, structure on the monoid, structure on the group. So there is a strong relation on the algebra with the type of solutions. So the algebra information gives me also solutions of a certain type, which is very strong. And this generalizes in some sense what is written there. Another thing is, once you have this in this situation, MXR is then automatically a submonoid of this group, which is not obvious. This is a localization, a central localization here. And you could wonder, what is the structure of this? And there have been many investigations on this. For example, we know it's a torsion-free group, finitely generated. You could wonder, is this ordered? One of the fundamental questions. You could wonder, when is it polycyclic by finite? So one can prove in this case, this is a result of Batchelor, Trudeau, and Vendramin, that this GXR is poly-infinite cyclic if and only if GXR is orderable, left orderable. Okay. Now, I will just talk about it. We can also determine, we determine basically the maximal condition is equivalent with being involutive. The question by Kateve-Isanova is, can you determine when you reach the minimum condition, the minimum dimension? We can give the minimum dimension is here, what was it again? 2x, 2 times the number of elements in x minus 1, if you walk square free. Square free means you have no relations where there's a square involved. Okay? If it's square free, we can determine exactly when this happens, and it exactly happens when it comes from the dihedral solution. It's uniquely determined in some sense. At the A monoid level, at the structure group, then you have more possibilities. You have several solutions with the same A, but the actions might be determining something. I will skip that result. Also, in the non-square free case, we know this also. But because of this conference, I want to make the link with group rings and get you alive again, or awake, or interested in this stuff. I will not do a lot, but I think it's an interesting problem. Some of my PhD students know, and I try to get them excited to get solutions, but here in India, there are so many people interested in group rings. You're smarter than us, so maybe you can solve this. Okay? Maybe you don't find it boring and then forget it. So now I want to come to the word brace and group ring. Okay. So I told you that the structure group is something like this. I forgot one word over there. in this case, the A is a free abelian monoid of rank the number of elements in X. In this case, the A is a free abelian monoid. So I'm going to restrict to that case. So A here is a free abelian, I'll do it with the group, so a free abelian group on so many letters. Okay, so it comes from involutive solutions. Okay, so the elements here you can write uniquely in this way. That's a unique way of writing elements. And in the free abelian monoid, I write the operation as an addition. Okay? And here I write the multiplicative. And I live in the semi-direct product, right? So you have to look at this in the semi-direct product with an action of the permutation groups. And this lives in the symmetric group on X. So they act naturally on the generators. Okay. Now, using this thing, I define a new operation by the one co-cycle. And the new operation is by definition A plus B in the first coordinate. And the second coordinate is uniquely determined by this. It's phi of A plus B. So this defines a new operation on this set. So I have this new operation plus, and I had the original product. And now you can verify in this thing easily. It's an exercise, and a very easy exercise. If I take three elements, and I'll simplify them as X, Y, and Z. So X, Y, and Z are in G. And with these definitions, you calculate that this is the same as, if I add X, it's the same as X times Y plus X times Z. This is the one co-cycle thing that gives you this, but you can easily verify it by hand. You don't have to know anything else. This is the definition of a left brace. So abstractly, I give you a group G with two operations. This is an abelian group, and I have a multiplicative group. With the following compatibility condition, exactly that condition. Then this is called a left brace. A notion invented by Wolfgang Rump, I think in 2007 or 2008. And since then, this work has exploded. This is an exponential growth at the moment, not polynomial time. Okay. You can define similarly right brace by putting these things on the other side. And a two-sided brace is a left brace that for the same operations is the right brace. And very recently, a bright young student of Agata Smoktanovich, his name is Lau, proved that a two-sided brace is such that if I look at this structure, G with a plus and the new operation, a star operation, and what is star? A star B is AB minus A minus B. String theorists know where this comes from. This is from radical theory. What he proves is that this is two-sided brace, even though if this is associative, and that is nothing else than saying this is a radical ring. Ring is associative, what I mean here. This doesn't have an identity, a radical ring. So left braces are extensions of radical rings. Two-sided braces are exactly radical rings. Okay? Good. Now, why do I talk about braces? I will not state it here, but you can reduce the description of all set-theoretic solutions that are non-degenerate and involutive, bijective, are unique. You can construct all the solutions if you know all finite braces, left braces. For describing all finite left braces, we have a constructive method to find all static solutions that are non-degenerate and involutive, bijective, of course. So it's very relevant to classify the left braces. The first step, if you're in a new category, is describe the simplest objects. Simple left braces. Naively, we thought, probably as in group theory, because you think maybe it's group theory we do. On the other hand, maybe it's ring theory. We know it's cohomology. It's linked with everything. But naively, you think, well, from group theory, simple braces, simple groups, there are not too many, especially in the finite case. Well, recently we proved there are immensely many. I'm not going to state it down. I can answer it later if you want. There are lots. So it looks to us, and we all constructed them from one specific type of construction, some kind of skewed version of a semi-direct product. There are lots. So the hope to classify them was a bit depressing at the moment, but if you have a dream, maybe the only method we know is the only method that should exist. I don't know, but that is, I think, not true. But let me now make you the link with left braces. How do you find left braces? So I'm going to talk about the group with an additive structure and a multiplicative structure. So I want to know, if you have a group with a multiplicative structure, when can you put there an additive structure on to make it a left brace? And it gives me solutions. So let me formulate equivalent conditions, and then I come to group rings. So now you should come alive. So equivalent conditions. First, it's a left brace. Secondly, T is a regular, I already alluded to that, is a regular submonoid of the holomorph abelian group. As I alluded to that before, but this is not really what you might get excited in. Funny thing is there exists a morphism from the multiplicative group to the symmetric group composition, such that f of fx inverse applied to y is equal to y of fx inverse applied to x. So some type of Cayley theorem, not necessarily a monomorphism, but with a funny condition. But again, that's not what I want to do. The fourth one is what I want to link in this conference. This was proved by Sisak. This was in 2010, 2011, I think. And this is hopefully exciting. So G dot is the multiplicative group of a left brace. I write it on the other blackboard. Even though if there exists a left ideal of ZG, the left ideal has to live in the augmentation ideal of G. Use Engel's notation, which I do not like, but it's the augmentation ideal of G, such that, first of all, the augmentation of ideal of ZG is equal to G minus 1 plus L, sums of two sets, and two, the intersection is trivial. Link this with the units, easy exercise. Hence, in this case, if I look to the augmented units, this becomes G times 1 plus L intersects the units of G. And the intersection is trivial. So what I get here is I get a complement of the trivial units. I haven't said a normal complement, I said a complement. And you have to keep in mind, I work with left stuff. I'm politically left-wing, so I write this on the left side. So this is a complement, trivial units. If I have a two-sided brace, so if with the multiplicative group of a two-sided brace, I told you this corresponds to radical rings. That means that your group G becomes the adjoint group of a radical ring. And there is a very old result of Sandling. He proves the isomorphism problem for such groups. The first step in that proof is finding a complement. This you get for free, because this proof is really very easy. You get this for free from the brace structure. And now you have to do a little bit more work. You work with some finite rings that are uniquely determined under isomorphisms, and you get Sandling's result back. So for me, an open problem is, and you with many, what the heck can we do with this in general? If G is a multiplicative group of a left brace, and there are many groups that have this property, can we prove maybe that this is a normal complement, even if it's not a two-sided brace? I have no idea. Can we at least calculate examples that tells us something? We can construct, if it's a multiplicative group of left brace, I can construct you what the generators of this are, but now you have to start playing with it. What can you do with this? Even if G is a nilpotent group, many nilpotent groups, finite, are left braces. There are counterexamples, not all of them are. There are counterexamples by Batchelor. Even if it's a nilpotent group, even of class 3, can you find a normal complement in this way? This is an open problem in Sudarshan Segal's book. We know the isomorphism problem holds for nilpotent groups. For me, it's a beautiful result and a beautiful thing, but it's still a black box. Can you do this for nilpotent groups, even class 3, and maybe make the black box a bit whiter? That's a general problem. And I wish I can solve something and do something with it, but I throw it in the audience, and I stop here. Thank you.